Good morning. So, last week or last lecture rather, we have seen a general introduction and we have introduced what are called semi-norms. The reason is that there are many spaces for which you may not be able to define norms or other metrics or anything. The second reason is that we want non-trivial dual. This is an important thing you want to learn it. Okay. So, we have defined a concept of a semi-norm. Now, we will see what is a semi-norm relay. So, we will continue the lecture. So, we will define start with a definition today, semi-normed linear spaces. Okay. A linear space again, a linear space. So, I said we are only considering linear spaces. That means there is a linear space X is called a semi-normed linear space, semi-normed linear space. Read the definitions carefully. Linear space, semi-normed linear space. Okay. If there is a family, P of semi-norms, is not just one with an index set. Index set can be singleton, countable or uncountable. Family P of semi-norms. I is an index set. Okay. Such that you need one property to be satisfied, such that P beta of x equal to 0 for all beta in I. Keep that if it is a semi-norm, single semi-norm for which Px equal to 0 implies x equal to 0, if that is satisfied, then it will become a norm. So, the only difference from semi-norm to norm is Px equal to 0 may not imply x equal to 0. But we are not demanding for that for every element in that, that means every element in the family. But if P beta of x equal to 0 for every every beta in I, then we are defining x equal to 0. So, in some sense you need that property. That means if intersection, if x is in the intersection of b beta of x equal to 0, then you need x to be 0. This is also called separating property basically. You will see that eventually using that you can define a semi-normed, it can make it a locally convex topological vector spaces and it defines a host of topology. So, to do that host of topology, to get a host of topology is precisely the kind of separating property you need it. So, a family with a property. So, the family of semi-norm with the separating property, if you can produce that, then X is called a thing. Indeed, if I is singleton, I is singleton, then there is only one element and the separating property is that Px equal to 0 implies x equal to 0, that makes X is a normed linear space. You see, you get that immediately. Okay. So, let us do something more. So, as I said, we make not rather we make the P defines a topology. We will define how a topology is defined. Topology on X which is a locally convex topological linear space with a host of topology which we will define. Okay. So, let me give this definition. So, let me start with what is this locally convex. Okay, locally convex topological space. A topological linear space, topological linear space X is called locally convex, if X has a base, if X has a local base consisting of convex neighborhoods. So, that is the thing. So, you have for points you get a neighborhood system which generates the topology, the local base consisting of convex elements. Okay. If XP X with a be a semi-normed linear space where P is the separating family, where P is the separating family of semi-norms so maybe not if, because there are many things to say. So, let X be a defined family. Semi-norms we define now we define a neighborhood system. We define a neighborhood system as follows. Probably to learn your distribution theory course, these details are may not be, all these minute details may not be necessary, but it is nice to improve your knowledge about the space better and it will help you. Okay. That is why we thought we will introduce this, otherwise this may not be seen in a normal functional analysis course in detail. There are books, few books where it is available, but most of the functional analysis books this may not be available in detail. Okay. System as follows. That is why we thought spending 1 hour or so, a couple of lectures is done. So, what do you choose? Choose let X be in X and choose any epsilon positive and a positive integer m, okay, and Pi belongs to P, where Pi's are semi-norms for finitely many. Okay. Okay. Define a neighborhood of X, we call this is a neighborhood of F, that is a definition, as U of X, this is a neighborhood X, it based on X closer, and that is how do you do. How do you define a neighborhood of for if X is a normed linear space? A neighborhood is something like BRX, right? This is a set of all y such that norm of y minus x less than r. That is what you do it, epsilon or. So, you get a neighborhood of X. So, you take all that neighborhoods which generate the topology. That is what you do it here also. So, it depends on P1 etc. Pm. So I have to use that. I will make a remark soon. So that see, this is set of all y in x such that your pi of x minus y less than epsilon for I equal to 1 to m. So once you fix that one, you get a neighborhood. So collect that neighborhoods. So with that define a local system, local neighborhood system. Define a local neighborhood system u at p, that is of x, is equal to, you collect all such neighborhoods, all possible neighborhoods, epsilon p1 etc. pm. What are the things varying? You vary all epsilon positive, you vary for all m in n, and then choose all the possible p1 etc. pm from p. Okay. So you are varying epsilon thing, that is what you do here, because here there is only one norm here. So if you vary, you get all the neighborhoods systems of that, and you do not have many things to vary, and this forms a neighborhood system at the point x. Now define, third one, define u at p is equal to union of p at x where x vary is a base for a topology, is a base for a host of topology. I will not prove all that you know how to prove it, how to generate. Once you give a base, you know that one. Host of topology on x. Host of topology on x. So that is where you get your base consisting of convex sets. Okay. So yeah, one remark I want to make. Remark at this stage, there is a minute subtle mistake you made. It is not enough to consider, it is not enough to consider only neighborhood of the form, neighborhoods of the form, okay, u x epsilon p. Okay. This is important because if you take two such things, u epsilon x p1 and u epsilon x p2, and its intersections may not have neighborhoods of that kind of forms. So it is important to take all possible finitely many things, not just one thing. So with this I can so you can if you want, you can explore more details, all the topology, all the open sets, all that, but what is more important to us in this course is about the convergence. Okay. So with that, if you are not convinced, I would like you to understand this is the convergence provided, because this we are going to use it for our spaces now. So we are given a very general thing. If you have a separating family of semi-norms, that generates a topology, host of topology. We will be considering very specific examples, and then this convergence is important, and this convergence is the one, and you have to write down the convergence for that specific spaces, and that is what we will be using throughout your course. Let xp be a normed, semi-normed linear semi-normed linear space, and we write it in a general form x alpha is a net. I am writing net, the reason is that there is no matrizability or counterability of anything. Okay. So, most of the time in our thing what we are going to study, most of the things will be under convergence only, but let me give you the definition thing, because there is no difference in that one. Then why I am using the net? Then x alpha converges to x if and only if limit alpha p of x minus x alpha minus x to 0 happens for all p in P. So, you see for all seminomes this happens. As I said, you will see more examples related to that. So, with this general definition we may move on to now very specific examples. So, let me take a new page. Examples of, these are main part of our discussion, examples of semi-normed linear spaces. Okay. So, again let us go back. So, recall, this is what we want to define, right? We want to define topologies on Cm of omega, C infinity of omega. C infinity we will come later. So, we will first make these things. So, you recall first AB. So, let us again motivate C of AB, recall, take C or consider C of AB. So, you have an AB here. As I said, you can't take the supernome norm f at 0, because that will not be finite. So, if I take any closed interval inside, if I click a closed interval a1 b1, okay, that is the closed interval a1 b1 contained in AB, then what we do? So, I can define PF, define P of f is equal to the supremum of, the problem is openness to make this finite. So, but if I take supremum of x is equal to in a1 b1, open or does not matter, because it is completely inside. So, even in open a1 b1 it will be finite. Okay. So, it will be the same, the supremum, because a1 b1 is completely inside. So, you have to do that. This is finite. So, if I restrict any compact, this is the concept we are going to use in the next couple of lectures. The whole thing about the using compactness, we are going to cover your open sets. That is what the property is. A semi-norm on CAB. Okay, is a, you can easily check that, because it is essentially the norm. The problem is semi-norm on C of AB, right. But PF equal to 0 will only imply F equal to 0, identically 0 on A1 B1, that is fine, but not on, need not be, that is been, not on, this will not imply, it may be or may not be, not on AB, you see. So, the thing is that here A1 B1 it will become 0, this will be 0 here, but you may not know what happens there, because that does not have that information, you see. So, it will not give you. So, that A1 B1 goes, you get more and more closer to it. So, it is a semi-norm that. Okay. So, this can be extended to for more general sets. Okay. So, I can define now Cm. So, this same philosophy we will do on Cm of omega. So, and K, where omega is a subset of Rn and K subset of omega compact. You see. So, I can define Cm for m is an integer including 0. This is also called C0. C and C0 of AB are the same. N is in M0 if you want it. Okay. So, I can define omega k set of all f in Cm of omega with the support of f compact. Okay. On this I can define a norm because k is compact. So, the support is only in k. So, I can define norm f at m to make it precise. I can put it also on k because you do not need that k, okay, because even if you take from here. So, you are basically taking for f here. So, it is a support in k. So, outside k. So, whether this you write it, whether you write this one does not matter because we are taking f from there and it will be the same because outside of the k you will not have anything. So, this is nothing but you can define two ways. So, either summation take all the derivative or you take the supremum, both are same, okay, both are equivalent, that is what I say. So, let me write it in the supremum form where x is in k and either you can sum or you take it this way for that. So, this is the norm. So, this is a norm there. So, Cm, okay. So, this is a norm. So, Cm with this norm. So, Cm omega k. So, this is also denote my norm f at m. I told you it is a no, basically norm at m. So, it does not matter, but this norm, okay, is a normed linear space. That is not a problem because you are considering only functions there and you get that one. But what you get is that you can also see this one norm f at mk in view of what is discussed here. You can see that norm f at mk is a semi-norm in Cm of omega, you see. So, what I am when you are taking a function in Cm of omega, so writing k is important in this because I am doing that only restricted to there. It is exactly writing my Pf here. So, you see I am taking Cm only there. So, this is what you have to understand. So, this is a semi-norm here, very important, and this will imply. So, only norm f, so norm f at mk, because in that case if for f in Cm, okay, this will equal to 0 will only imply f equal to 0 on k, not in omega. Okay. So, that is the first thing you want to do it. All right. So, I can define so this is a family of semi norms. Now, I use my thing. So, you have a, this is the whole thing I am going to use it in the entire thing. So, you have an omega is a subset of Rn and Rn is a para compact thing. So, I can write my omega is equal to union of kj where j is equal to 1 to infinity, and I also take an increasing, this is a increasing sequence of compact sets. kj plus 1. So, now you have to be bit alert, because there are variation m and kj's, there are two things are coming when you go to C infinity. So, to keep track of your index very carefully when we say continuous embeddings and all that. Okay. These are compact. So, what you are doing is that you are taking k1, then you take k2 like that, it will go k2 like that, it will go, you get some kj. Okay, so, that is what you are doing, and you can write down, that is a kind of para compactness on that one. So, on that, so I will define seminomes now. You already define. So, for each kj I define a, we already got a, for each k it is a seminome. Now, for each kj I get a seminomes, taking care of all the elements of omega. Okay. Otherwise, if you just fix a k, you do not know what happens outside that one. Okay. Seminomes pj on Cm of omega to r by the same thing pj of phi. So, the same thing is nothing but norm of phi at m kj. So, on each kj I am taking. Okay. So, that is nothing but, once more I am writing, because these are all you have to get familiarized with it. So, d power alpha of phi x, okay, where mod alpha less than or equal to m and x is in kj. So, this is a clear thing, I do not want to call it even an exercise, but if you are first time see, is better that you verify. Okay. If pj of phi equal to 0 for all j. So, you are getting a countable family, your index set is a countable family, infinite family, because omega is open and the kj's will be an increasing family of countable. You can do that countable representation of omega with compact sets. Okay, that is a property of Rn. Okay. J equal to 1, 2, etc. will imply phi identically 0 in omega. That is a trivial thing, because if you take any point there and kj's are increasing, and so that it will eventually subsume x is in omega, x will be in kj for some j, and you get for pj of that one. Okay. So, so if bj of phi equal to 0 and you get x equal to 0, phi is identically 0. So, for every phi you will get it. That implies, this is a family, that implies p is equal to pj, where j equal to 1, 2, etc. is a separating family, you see, very nicely separating family on Cm of omega. Okay. So, let us see how far I can go today. So, now you know everything basically, because once you have a defined a topology, this one Cm of omega p, we have developed the neighborhood system for general semi-normal linear spaces. So, generates a locally convex topological, locally convex topological linear space. So, Cm is a, which is a host topology. So, that way you get topologies on including for all m equal to 0, 1. That is why the notation I given C naught is C. Okay, 1, 2. So, all that. So, let me write down the convergence in this one, and then probably I do not know I will stop it or not. Okay. So, let me write down the convergence. I thought I will finish little more. Maybe I will with this I will finish, so I will start. So, I will write down the convergence on This is important, this you shouldn't forget, whether you know understand the topology or not, whether you are studying the topology or not, this convergence will that one. So, let a phi L phi belongs to Cm of omega, then the same topology you write it. So, it is nothing new, phi L converges to phi in Cm of omega if and only if. So, this understanding this is better, and only if d power alpha of phi n converges to d power alpha of phi uniformly on compact sets, okay, uniformly on compact sets for all compact sets in of course compact sets in omega, if you want that, for all alpha multi indices at the for which mode alpha less than or equal to m. Okay. And other thing you can see that the identity I from Cm plus 1 is contained in Cm, right. So, Cm, note that Cm plus 1 of omega is contained in Cm because this m times so you can define an identity mapping and you have the topology Cm thing is continuous. So, that is continuous. So, we can write that when Cm plus 1 of omega continuously contained in. So, that is why when there is identity mapping continuity is called that one is continuous. So, this is what you say that this is embedded continuously, embedded continuously. So, so next step is to prove for C infinity also. You can tell few words, maybe I will start. So, get familiarized with that one, and you need an another infinite collection double sequence, and then we will do that in the next class. Okay. Thank you.